Welcome to episode 54 of Fresh Thinking with Optiro. I'm Ian Glacken. I'm an executive consultant here in Perth, Western Australia. I'm joined today by Dr. Oscar Rondon. Oscar is a very experienced geostatistician. He's got a PhD in mathematics and geostatistics, and he is part of the supervisor team. He also provides a lot of support to the Snowden Optiro consultants with respect to geostatistics. Today we're going to talk in two episodes about applications of conditional simulation. So I might just start. Welcome, Oscar.
Thank you, Ian.
Sorry. I might just start by very quickly breaking down what conditional simulation is without going into a MSc level detail. So the words are the key: conditional and simulation. Conditional means that what we're producing honours the data, specifically the histogram of the data, the variogram, and if we're dealing with multivariate, in other words, multiple elements, it also honours the relationships, the correlation coefficient between various elements, and also the variogram between the various elements. And then the second word is simulation. Simulation essentially means that we've got the element of randomness. In other words, we're using some sort of random number generator, which may sound horrific, but it actually works quite well in practice. So one of the key concepts in simulation is this idea of the space of uncertainty. Oscar, could you tell us about that, space of uncertainty?
Yeah, in very simple words, the space of uncertainty could be what is the range of possible outcomes for a given location. Let's say that we got a block model. In one block now with conditional simulation, we may have a range of possible grades for that block. Yeah, that's one way. If you look, that's on a local scale. If you look on the global scale, you can report your conditional simulations, the grade tonnage score, and then you have a range of potential grade tonnage score for your deposit. That's another way to treat this space of uncertainty.
Yes, I know that some people get quite heated about this, and I guess the main concept here would be is if you generate a number of realisations or simulation models, say 50, and you've got a certain amount of variability, grade variability, and if you do some more and that grade variability increases, then you probably haven't reached the space of uncertainty. So generally it's quite easy to work out what we're doing here. So what I would say about simulation is we're attempting to quantify grade uncertainty or multiple grades, but also what we're trying to do is attempting to quantify geological uncertainty, and that's a much more difficult task. And we might talk in this podcast or another one about how we can capture geological uncertainty. So let's move on to applications of simulation. So the main application is where we look at a group or a suite of realisations. I use the word realisation not to be confused with a simulation. A simulation is the group of realisations. A realisation is an individual model. So we might generate a simulation of copper grade, say, and we might have 60 or 70 realisations. That means we have 60 or 70 individual models of copper grade or whatever. So a lot of applications of simulation, in fact the majority would really relate to looking at the group or suite of realisations. So Oscar, what can you tell us about some of the things that we might look at in this area?
Yeah, as I mentioned before, Ian, when you look at a simulation, a condition simulation, as you explained, you have a whole range of possible values, right? So we need to be really careful. I would like to take the opportunity to mention that simulation is a lot of work, right? And we cannot use, in most instances, just one simulation. So given the range of simulation, as I mentioned before, can give you possible outcomes that you need to analyze. In few special cases, we can use a single realization, as you pointed out. Yeah.
So what sort of statistics or work can we do with the suite of realizations?
It depends on how you want to use the simulations, right? So for instance, as I mentioned before, if you want to look at the uncertainty in grade tonnage curve, you can use all of them. Sometimes you need, like as you mentioned, like a transfer function or something to get information and reduce the amount of simulation. You can get a criteria, and then you report your P90, P50, and P10, which is the...
So let me stop you there. You mentioned the word transfer function. I think our listeners might not be 100% comfortable with what that means. So what's a transfer function?
For instance, it depends on the application. A transfer function, a very simple transfer function, can be the grade tonnage curve, right? So you report all of them, and then you get the one that produces, let's say, the highest metal or close to the highest. That's P90, the medium P50, and the lowest P10. That could be a transfer function.
But it can also be some quite complicated stuff like pit optimization,
or
even a metallurgical flow sheet, or even an NPV, as you mentioned.
Right.
So that's what we can do with these range of simulations. And as I mentioned to you, this is by far the most common set of applications of simulations. For instance, we might use it to work out the best stockpile size for a mine. We might want to look at the range of sizes of open pits. We might want to look at the range of sizes of stopes. So there's a lot of applications of this idea where we're looking at a suite or a group of realizations. One thing I should say, and we probably should have said this right up front, is that simulation is not the same as estimation. Okay, they're two different things, and they have a very different purposes. Oscar, you have some views on this.
Yes. What we need to remember is that estimation, let's say kriging was designed to minimize the variance, right? So at a given block, when we run the estimation, the theoretical property of kriging minimizes the error, so the estimation variance. Conditional simulation is quite different. So at a given block, we try to reproduce the data distribution. So we are not minimizing that variance. We have now a range of possible values. That's the main difference between conditional simulation and estimation.
Yes, and of course, you can actually get a group of realizations and simply average them, and this gives what's called the E-type. Now, in most circumstances, if you're declustering correctly, the E-type will approximate the grade estimation. But of course, why bother? Why bother generating 50, 60, 100 realizations if you're just going to average them? So I think it's very important that we consider that simulation has a very different purpose to estimation. We're looking at uncertainty in grade and uncertainty in geology.
I would like to add, Ian, now that you mentioned that, during the training courses, when we are presenting conditional simulation, some practitioners ask, what happens if I have 100 estimation techniques? Do I have a conditional simulation? No. Okay? Because if you have 100 different estimation techniques, you have 100 estimated values. So you won't be able to reproduce the variability.
Yeah, so it's important to understand that difference between simulation and estimation. Estimation, as you mentioned, we're looking for the minimum error. Simulation certainly doesn't give you the minimum error, but what it will give you, under the right circumstances, it will give you an appreciation of the grade uncertainty. Now, one of the challenges facing the mining industry is capturing geological uncertainty. Now, you can imagine that grade uncertainty is a relatively easy task, but geological uncertainty is much more difficult, primarily because every ore body is different, and the degree of uncertainty is quite different. For instance, we might be looking at the depth to the top of a unit, or we might be looking at the thickness of a unit, or we might be looking at the position of faults. And it's quite a challenge, and there has been quite a lot of work on this, but a lot of work to go. It's quite a challenge to capture the geological uncertainty. So it's possible to simulate the geological uncertainty and then simulate the grade uncertainty. So how would we handle all that information, Oscar?
Yeah, the usual approach, Ian, is I tend to say, well, sometimes I say that simulation and estimation are similar in this way. So whatever we do in estimation, we need to run variograms, we need to have domains, we need to validate the data. That's exactly what we need to do with conditional simulation. And that means that when we are running the conditional simulation, we are running this on a domain-by-domain basis. So if we are planning to run a geological simulation, we need to first have those domains. We need techniques to simulate geology, And after the simulation of geology, then we need to simulate the grades inside each domain. So you can see it's a lot of work. And that's what I usually say, that before embarking in a conditional simulation study, you need to know exactly what you want to do. What is the target? What is the aim of that study? Because it's a lot of work.
Yes, a lot of people do a simulation and then they say, now what?
Exactly.
Just before we finish, I just wanted to talk about one particular application of multiple simulators and multiple realisations, and this is resource classification. There's a paper by Parker and Dome, 2014, and this talks about what might be termed the 90-15 approach. So the 90-15 approach basically says that if we're going to classify a bit of the ore body as measured, say, we need to have a 90% confidence that the grade is within 15% of the true value, whatever that is, on parcels that represent a month or a quarter. So this approach has been used, or it's been specified by most of the majors. And really, there's a few ways of doing it, but to do the job properly, you really need to look at a simulation of the grade variable. And of course, as Oscar mentioned, if you have a geological uncertainty, then you need to generate these pictures of geological uncertainty, and then within that you need to think about grade uncertainty. But this is a very common technique. More and more companies are starting to use simulation, and the main reason for that, of course, is that the computers are getting faster, the algorithms are getting more efficient, and the time taken for processing is much less. So we're seeing classification as one of the main tools for using simulations.
Now that you mentioned that, Ian, can you please comment on the difference between measure the classification, let's say in the JORC code, and the classifications used in simulation? Because they are quite different, right?
Yeah, I mean, don't really get me started on the JORC code, but the current version of the JORC code, which is 12 years old now, 2012, requires the competent person to make some statement on the accuracy or the precision of the simulations. Sorry, not of the simulations, of the resource report. So really the only way to properly do that is through simulation. Yeah. So what we're going to see next year being 2025, or maybe even this year, we're going to see a new version of the JORC code. And there's almost certain that will have more requirements, more declaration on the basis of uncertainty. And really, as we've mentioned, one of the only ways to generate this uncertainty is through simulation. Okay, so let's stop that there for now. We've got more to talk about, and we're going to talk about that in another podcast. If you enjoyed today's podcast, please subscribe to our YouTube channel or to Fresh Thinking by Snowden Optiro. You'll find this on the Snowden Optiro website, Spotify, Apple Podcasts, or wherever good podcasts are found. Thanks for joining us, and we look forward to having you join on our next episode, which is a further discussion of some of the applications of simulation.
Thank you.